Okay, welcome back, everyone. So as you can tell, I'm on a computer screen right now, and that's because, well, as I said in the previous video, I'm actually in Poland right now, so unfortunately I couldn't transport the board since it's just too big. So as a result, unless I somehow buy a board here, I doubt it, but for now we're going to resort to using the computer screen. So today we're actually gonna introduce a bit of differential equations, and specifically, our goal today is to find a pretty much foolproof way of solving linear differential equations, and specifically of order 1. And if you don't know what those things are, then I'm gonna explain some of the very important ideas that are essential to know throughout the course, throughout differential equations. So first, what are differential equations? That's what we mean by definition of differential equations. Well, all differential equations are is they're equations with derivatives. So I can give an example of a differential equation. For example, we can have like dy, so d squared y. That's not, I shouldn't be saying it like that, but this is essentially the second derivative of y with respect to x. Times, times, for example, xy squared. This is completely random. Plus dy dx times x equals, 0. So this is an example of a differential equation. Now, this one, there's probably no good way to solve it at the moment, but yeah, it was completely random. But as we'll see in this video, there's a specific form that we're going to be looking at, and those are linear differential equations, and we're also going to define nonlinear differential equations right here. But yeah, differential equations are heavy in application. So if you're an application type person, this is a course that's probably a necessity. Differential equations are all about modeling things. So like modeling fluid flows, modeling, for example, the motion of a pendulum, all things like that. Modeling they have heavy applications in thermodynamics and even climate change. So modeling climate patterns. So yeah, differential equations have a lot of applications. So that's kind of the motivation for differential equations. And the goal for differential equations, I guess I should definitely say that, is, well, if you look back at the equation that a random differential equation that I wrote out, the goal is to find what functions of y satisfy that. And yeah, that's basically the goal. And the thing about differential equations is, it seems like a very straightforward goal, but people spend a lifetime studying differential equations, so it's definitely not so simple in many cases. So what is the order of a differential equation? The order of a differential equation is the highest power derivative. So if we look back at that example, I'll just write down another arbitrary example. So d squared y dx squared plus dy dx x plus y, I guess, equals 0. Again, our goal would be to solve for y in terms of x here. So y equals some function of x. And in this case, we'll get to this in 1 second, but we're going to have intertwined here two constants of integration. Since our order is 2, this is what I mean. Since this is the highest power derivative, since 2 is the highest power derivative, our order is going to be 2. Similarly, if this term wasn't here, actually, I found a new way of erasing. Anyway, yeah. If this term wasn't here, try that again. Okay, then our order would just be 1. Okay, so that's fun. So I'm gonna get rid of this. And now, let's see, types of differential equations. Well, this is a pretty quick one. First, the ones I just showed you are ordinary differential equations. They just include normal derivatives, but there are also things called PDEs, or partial differential equations, which are equations that include partial derivatives. These are exponentially harder to solve than ODEs normally. There's an entire course that, well, there are entire courses that you take just on these. So yeah, they are. And people, people have their PhD, many people have their PhD in partial differential equations, studying them. In fact, Dr. Payam, if you know him, he's a fairly well-known math YouTuber. His PhD is in PDEs. So yeah. Now let's talk about linear versus nonlinear differential equations. Well, let's see. So what is a linear differential equation? And whatever it isn't, then that's a nonlinear differential equation. So what a linear differential equation is, well, I'm just going to kind of write out what it is right now, and I'm going to explain it. So kind of the abstract definition, then I'm going to explain it. So the nth derivative of y with respect to x, dn, and then we have some, let's call it f sub 1 or f sub n of x, plus all the way down, or maybe, I guess I'm losing a bit of structure here. Dx dn minus 1, fn minus 1 of x, plus all the way to, I think you get the structure. Basically down to there being no derivative, so just y itself. So some f sub 1. I guess we can think of that as the derivative, the 0th derivative. So it's actually f sub 0 of x, y, equals some other function of x, call it g of x. So this is this is the form of a linear differential equation. Well, I guess some counterexamples of a linear so what are nonlinear differential equations? Well, examples of those are ones where, let's say, our derivative, so we have like a dy dx, for example, is to a power of 2, and etc. But the problem is here, some people get this confused with the second derivative, but this is actually just okay. Sorry for that. So no matter what else we have here, we have this term, this derivative to a power which is not, not 0 or 1. So that is an issue. That means that this is already a nonlinear differential equation. Another counterexample is if we've tried everything to put it in a linear form, but we still have these functions of y in front of our derivatives. So let's say this was just dy dx, but we have like a function of y plus y times a function of x. No matter how we try to redeem ourselves to make this linear, we still have like a function of y in terms as a coefficient of the derivative, which is against the law of linear differential equations. So this is another nonlinear one. Oh, I thought that would work. I guess not. Okay, let me just get rid of some of this. Oops. Okay. Solutions to differential equations. Oh, I guess we already talked about that. They're essentially they're essentially y in terms of x. But now we talk about 1-parameter families and 2-parameter families. So this is related to how the opposite of a derivative is an antiderivative or an integral by the fundamental theorem of calculus, or one part of it. So, you know, if we have this very simple differential equation, dy dx equals, let's say x, well, I guess, I mean, you would do this in calculus too, but to solve this, well, we would just have dy equals dx. This is called a separable differential equation because we can separate out functions of y and functions of x. So, well, you can easily, what you do here is you integrate both sides. And when we integrate both sides, you have y equals 1/2 x squared plus c, this constant of integration. Actually, I need to figure out if I can, like, because I'm having this issue where I like that it's kind of aggravating. Wonder if there's a way to. Okay, fix it. Nice. All right, sorry for that. But it's this constant of integration that we're interested in, and well, if we had say 2 here, we would have to perform 2 integrals, and that would give us a c1 and a c2. So that's essentially the idea here. Yeah, so one parameter family is a family where the solution, so y in terms of x, is going to be some function of x plus a single constant of variation. So a single arbitrary constant. That's a one parameter family. A two parameter family is basically a solution to a second order differential equation. So we would have some function of x plus c1 plus c2. Now this is not rigorous at all because this assumes that, well, c1 and c2 aren't the coefficients of any functions of x. So to be more rigorous, we should also give them like possible coefficients. But I'm just writing that out just to get the idea down. So that's the idea for one parameter and two parameter families of solutions to differential equations. So particular solution. Now this goes along with this idea as well. You can think of this. Let's say this is like y equals x cubed plus c. Well, if we vary this x, we can, and we kind of like leave out a few solutions, because if we didn't leave out any like gaps between the c's, we would get the entire R2 plane filled. So if we leave some gaps, it's gonna like look a bit like this. This is hard to draw for me, so don't mind that. Because that happens. But you kind of get the idea. It's just, this goes up, you know, till infinity. This is not a good drawing. Something like that. Okay. Yeah, these are all. Yeah, these are supposed to be aligned nicely, but they're not. Anyway, that's the idea. And a particular solution, what that is where we are given that this function in terms of y goes through a specific point. So y of some x naught equals y naught. Now this should seem familiar from the very basics of differential equations, which should be taught in calculus 1. That's like initial value problems. So that's the basic stuff. So there's this, right? So then let's say this point is somewhere here. Then we single out this single curve from the rest of them. So this is the curve we choose. So this is our particular solution. And if we have two parameter family, then, well, we're going to need, you know, two initial conditions. So yeah, that's basically the idea. So let's continue here. All right. So we did particular solutions, explicit versus implicit. Okay, well, this is a really basic idea. It's, well, we already talked about explicit solutions. So what explicit solutions are are they basically what explicit solutions are, again, sorry, someone came into the room again, but what they are, basically, we just talked about them. They are solutions that we can simply get y in terms of x. It's the nicest case. But we can also have implicit solutions where we have y, we could have like our solution, which is, it's kind of hard to explain, but it's not as nice. So maybe an example would be like, I don't know, y cubed plus y ln y plus x squared equals 0. This doesn't have any, maybe like equals e to the x. This is super ugly. This doesn't have any derivatives in it, so it's a solution technically to a differential equation, but we can't, or at least there's no way, I think, to isolate y. That's the idea. So if we can define it implicitly, explicitly, I should say, y can be solved for in terms of x only, but we can't do that here, I'm pretty sure. So those are the uglier cases, plus c. They're realistically right. Okay. Let's see. So we can go through the rest of these fairly quickly. Trivial solution is just y equals 0. This doesn't have any c's in here, any c nonsense. It's just y equals 0. This is the trivial solution. The general solution. So a general solution, and this goes along with singular solution. So a general solution is a solution where we can define all solutions to a differential equation simply in terms of in terms of an equation with c's. And then singular solutions, this ties in again, are for example, y equals 0. They are solutions on their own where they are not in terms of c. So they are just on their own. They're singular, right? So ideally, we would want a differential equation to have a general solution, so that will describe all solutions to the differential equation. We don't want some kind of stray singular solutions. I'm going through this a bit quickly, but it's just to get the basic idea of what this is. Interval of definition. Well, it's kind of abstract, but it's essentially the largest interval on which the function, for now, let's just assume the function can be defined explicitly. The function y equals y of x. The largest interval where this function is defined. So like y equals 1 over x, let's say, plus c. Well, this is not defined at x equals 0. It's defined at negative infinity to 0, union 0, open brackets, by the way, to infinity. So there are two possible intervals, but if we're looking for the interval definition, basically most problems will just want you to choose one of these, since they, we can get kind of iffy with infinity, but we can think of them as having the same size in a sense. So we can choose either of them. I usually go with the positive because I think it looks better, but yeah, that's just personal preference. Okay, so finally, initial value problems. I gave one of them here. I'm not going to do any more of these since I personally think they're very basic. But here's an example. So we're given the differential equation, and in fact, you can see that, and I encourage you to see this yourself, but this is actually a nonlinear differential equation, because look at this square here. If this square wasn't here, then it would actually be a linear differential equation. So that's a nice extra exercise there. But we're given that the one parameter family, because there's one parameter, is y equals 1 over x squared plus c. So now our goal is to find c if possible, and the interval of definition if our initial condition is y of 0 equals -1. Okay. So how do we do this? So let's plug in this initial condition to find C. So what will that give us? Well, if we plug in this initial condition, we just have that -1 is going to be equal to 1 over C, because x, if we plug in 0 here, we get 0 squared, which is 0. And that just implies that C is -1. Using some basic algebra, but plugging that in, we have y equals 1 over x squared minus 1. Okay. Well, in order to find the interval definition, we're going to need to kind of graph this, right? To have an idea of what the graph is. Now, this graph is a bit tricky without a little bit of time, but the quick way to do this is to find asymptotes, perhaps, and then, use some skill, or a graphing calculator like Desmos would be helpful. But vertical asymptotes are when the denominator is 0, so that's at x equals -1 and 1. So this is 1, -1. And then we have our horizontal asymptote where if we take the limit of this as x goes to infinity, we'll just get y equals 0. So, and also because the degree of the denominator is larger than the degree of the numerator. And, if you try some points, perhaps, you can get that the graph. And honestly, you don't even have to try points. It should come pretty naturally that this graph will resemble something like this if you see these asymptotes. So it'll look something like this, right? So this point, note that this point is in fact -1, or sorry, 0, -1. And what does that tell us? Well, we have 3 possible intervals to choose from, but this is where our point lies. So we only have one choice here. We have to choose this interval. And what is that interval? It's from -1 to 1. So that is this problem finished. And in the next video, since this video is probably pretty long, well, in the next video, we're going to actually find a concrete way of solving linear differential equations of order 1. So kind of do a bit of a proof. And then we're going to, in the video after that, we're going to do some examples. So hope you enjoyed that video, and have a nice day. Goodbye.